How would you react if I told you that these 11 equations allow you to solve for 26 unknowns? If you've studied algebra before, you might be immediately suspicious of my claim. And for good reason. Generally speaking, you do need the same number of unknowns as equations in order to uniquely solve for all of them. However, in this puzzle I designed, it really is possible to do this, and I'm going to try to convince you that it's possible without giving away the solution. I'm also going to prove to you that 10 equations would be insufficient. I'm Andrew, and you're watching Bits, Bytes, and Bolts. The inspiration for this puzzle came from these puzzles that I remember seeing in math class as a kid. The goal is to find a numerical value for each of these shapes, according to this set of equations. These are great puzzles for getting students to think more symbolically about mathematics, but they're not particularly challenging for two main reasons. First of all, we have direct numerical answers to these equations, which almost immediately give us the value for one of our shapes. Second of all, once we have this first value, finding the values for the rest of the shapes is trivial by substitution. But what if we get rid of this numerical answer and keep all our equations purely symbolic? And what if instead of 3 shapes we consider the 26 letters from A to Z? What if we also insist that each letter correspond to a distinct integer between 1 and 26? And finally, what if we restrict our equations to simple addition, subtraction, multiplication, or division, with 2 letters on the left and 1 letter on the right? What's the smallest number of equations necessary to guarantee a single unique solution to the puzzle? As you might have guessed, it's 11, and here they are again. Now, if you're a puzzling purist, you should probably pause the video now and try to solve this yourself, before I say anything that might steer you in a particular direction. For those of you that solved it, congratulations. Maybe just leave the video running in the background for me. For everyone else, you might be wondering how it's even possible to do better than the standard algebraic rule of n equations for n unknowns. This is a perfectly natural question, so let's first make sure we can in fact do this with 26 equations. Feel free to pause and try it yourself. One way to do it is to start with a times a equals a, which is only possible when a equals 1, and from there simply count up to the rest of the numbers. A plus a equals b, so b is 2, a plus b equals c, so c is 3, and so on all the way until a plus y equals z, where z is 26. You might notice that this last equation isn't actually necessary in this case, since every equation before it gives us the value for one new letter. We know that no 2 letters can share the same value, and there are only 26 integers to choose from, so we can deduce what z is by process of elimination. And this is true in general. We don't even need all the letters to appear in the equations, as long as all but one of them do, and we can uniquely solve for those. We cannot pull this trick with 2 letters left over, since we could assign either letter to either of the 2 leftover numbers, and both solutions would be equally valid according to the information we have. For this reason, we can't possibly imagine solving this puzzle with only 8 equations, since that would only give us 24 letters and leave 2 out. But what about 9 equations, or 10? What's so special about 11 equations? To understand that, we first need to understand what other tricks we can pull to do better than 25 equations. A great way to get a feel for this is to solve a smaller version of the problem first. Just consider the 6 letters A through F corresponding to the numbers 1 through 6. This one is possible with only 2 equations. Feel free to pause and try to find them. Here's what I came up with. A times B equals C, and A plus D equals E. If you stare at this, you might convince yourself that the only way to multiply 2 different numbers between 1 and 6 and get a third different number between 1 and 6 is if the numbers are 2, 3, and 6. Or 3, 2, and 6. We can't distinguish A and B because multiplication, like addition, is commutative. 2 times 3 equals 3 times 2. This is essentially the same as the problem of leaving 2 letters out of our equations. There isn't enough information to get a single unique solution. However, since A also appears in the second equation, we have different information about A and B overall, thus breaking the symmetry between them. And here you might realize that the only way to add a number we have not yet used to either 2 or 3 and get another number we haven't used is if the equation is 3 plus 1 equals 4. So there we have it. A equals 3, B equals 2, C equals 6, D equals 1, E equals 4, and by process of elimination, F equals 5. There are 2 key takeaways here. The first takeaway is that there just aren't that many ways to combine the integers from 1 to n into valid equations. It's even harder for multiplication than it is for addition, since the answers grow faster. For example, in our 26-letter puzzle, the equation a times b equals c cannot possibly contain any number greater than 13, which cuts the search space for those values in half. 14 times 1 equals 14, which means our equation would really be a times b equals a, and 14 times 2 is already greater than 26. When I was designing these puzzles, I found it very helpful to start with the multiplication equations, and I highly recommend doing the same when trying to solve them, as you can narrow down the options very quickly. By the way, the restricted set of sequential integer values is why these puzzles can quote-unquote break algebra. Normally, in an algebraic system of equations, there are no restrictions on variable values, and you really do need all those equations to obtain a unique solution. But here, this added constraint allows for much more compact systems. The second takeaway is that symmetry is the enemy of uniqueness. Whether it's two letters left out of the equations or two terms in a commutative operation like multiplication or addition, if we know exactly the same information about both of them, we'll never be able to tell them apart. Subtraction and division, while not commutative, don't save us. In fact, you might have noticed I've been ignoring them, and that's because a minus b equals c is exactly equivalent to b plus c equals a. Likewise, a divided by b equals c is exactly equivalent to b times c equals a. We can always rewrite subtraction and division equations as addition and multiplication equations, and since those are commutative, the symmetry is much easier to see. This concept of ambiguity from symmetry extends beyond pairs of letters, however. To generalize it and to understand in the most intuitive and elegant way why 10 equations will never work, we need to stop viewing these systems as written equations and instead view them as graphs. To do this, let's turn each letter into a vertex, or node, and connect them with edges, or lines, according to how they're related to each other. Since a and b multiply together to yield c, we'll connect a to b with a magenta line labeled f for factor, and we'll connect both of them to c with orange lines labeled p for product. Then, since a and d add together to yield e, we'll connect a to d with a green line labeled t for term, and we'll connect both of them to e with blue lines labeled s for sum. Since f isn't part of any equation, it remains an isolated vertex with no edges. Hopefully you can see that this graph contains exactly the same information as our written system of equations, but now the relationships between the equations are much easier to see, and it only gets more helpful for larger and more complicated systems. Earlier, when I was describing the problem of symmetry, I said that if we know exactly the same information about two letters, we'll never be able to distinguish them. Well, the information about a letter is just how its corresponding vertex is connected to the rest of the graph. Not only its immediate edges, but the entire structure it's embedded within. If two letters are informationally indistinguishable, then if I were to hide all the letters in the graph, you wouldn't be able to tell their vertices apart by the structure and edge colors alone. Note that how I draw the graph is irrelevant and can't be used as a hint. Graph theory only cares about the underlying structure of the connections, not how we arrange the graph spatially when we visualize it. A more whimsical way to think about this is to imagine we give our little bitbug a list of all the written equations, then let it explore an unlabeled graph of those equations. If we asked it to label an indistinguishable vertex, bitbug wouldn't be able to narrow it down to one correct answer, no matter how much it explored the graph and charted its connections. For example, if it only had this multiplication equation, it couldn't uniquely label a and b, just like how we couldn't uniquely set them to 2 and 3 versus 3 and 2 earlier. However, it can see that only one of them is also connected to this addition equation, so it knows that one must be a, and it can label the rest of the graph with similar logic. Let's look at some graphs of puzzles that can be uniquely labeled and uniquely solved everywhere except for a single symmetry, yielding 2 solutions overall. I will be showing the solutions, so prepare to promptly pause if you want to try to solve any of them first. The case of 2 letters left out is by far the simplest. Neither letter is connected to anything, so naturally we have the same information about both. Here's an 11-letter puzzle where the main connected component is exactly solvable, but where we cannot uniquely assign the last 2 letters j and k. We've already seen this next case of a commutative equation with no additional information to distinguish its terms or factors, the simplest example of which is the single equation a plus b equals c for a 3-letter puzzle. I should note that even though graph theory doesn't care about how we draw the graph, it's helpful to use the bilateral symmetry of the triangle here to make this structural ambiguity easier to see. We could flip the triangle horizontally and it would look exactly the same. Here's a 10-letter puzzle with this same kind of undetermined equation. You can almost think of spinning this triangle around the single vertex that connects it to the rest of the graph. There are no other connections to tether this structure to one particular solution over another. We can also have symmetrical structures that are larger than single triangles. Here's an example of that with 7 letters. In this case, the entire graph is bilaterally symmetrical, and flipping it left to right yields a structurally identical graph. We can even have entire islands that are identical in a graph with multiple connected components. We've already technically seen this in the case of 2 letters left out, but here's a 20-letter puzzle with larger and more interesting islands. Now our poor little bitbug, exploring this archipelago, wouldn't even be able to tell us which island it's on, much less which vertex. Finally, it's worth noting that completely avoiding all these types of symmetry is a necessary but insufficient criterion for a puzzle to have a single unique solution. In other words, even if our little bitbug can correctly label all the vertices with their letters based on the set of equations, there still may not be one numerical mapping that actually solves the puzzle. Here's an example of a puzzle that follows all the rules, but it has 3 valid solutions. Here's one with no solutions. But when the stars align, it's just beautiful. Here's the graph of our 11-equation, 26-letter puzzle, rewritten with only multiplication and addition, containing no symmetry at any level. No identical islands, no mirrored groups, no undetermined equations, and only one isolated vertex. So with everything we've learned, let's attempt to construct a 10-equation, 26-letter puzzle. By walking through everything that must be true about it, we'll arrive naturally at a logical contradiction. Number 1. We only need to consider addition and multiplication equations, since subtraction and division are informationally equivalent. I'll use this small circle to denote either addition or multiplication. Number 2. We need a minimum of 25 letters represented in the equations. Number 3. Since 10 equations give us 30 spaces, 5 letters can appear twice, with the other 20 appearing only once. Number 4. Since addition and multiplication are both commutative, one of the terms or factors on the left-hand side of each equation must appear elsewhere in the system. Number 5. Combining 3 and 4, we have exactly enough spaces to make 5 connected pairs of equations. Equivalently, our graph must be comprised of 5 disjoint islands of this form. Number 6. No island in the graph can be symmetrical. In other words, we cannot have 2 addition equations or 2 multiplication equations connected together, since this would result in bilateral symmetry. This leaves only an addition equation connected to a multiplication equation. And finally, the contradiction. Number 7. No islands in the graph can be identical. We only have one valid type of island, and we need 5 different ones. We'll never be able to do it. So there you have it. 10 equations are insufficient to create this puzzle. If you ask me, it's pretty amazing that adding one more equation gives us enough flexibility to make a graph with no symmetry at all, given how cramped the 10-equation problem seems. I sincerely hope you enjoyed our little adventure today, and maybe you learned something new about bending the rules of mathematics to make interesting puzzles. Let me know your thoughts in the comments below, and until next time, this has been Bits, Bytes, and Bolts.